Hello everyone. I'm Yunhe Wang. Thanks very much to organizers for their hard work, and very glad to see you at the workshop at Accelerator. Today, I'm happy to introduce you the adder neural network, a new kind of deep learning paradigm with only additions, so that we can reduce the costs for launching them in terms of both energy consumption and circuit areas. And first, I would like to briefly introduce myself. I'm currently a senior researcher at Huawei Noazak Lab. At there, working with several colleagues on the research of computer vision and deep learning. Before that, I got my PhD degree from the Peking University under the supervision by Professor Chao Xu and Da Chengtao. The topic of my PhD is the method about how to compress and accelerate deep neural networks, and it is also very happy to me that I can continue the research in Huawei. So my main research interests are also the model compression, low-cost deep learning, and computer vision. Basically, all of these techniques are developed for reducing the expensive costs required by recent deep models, and wherein AdderNet is a very special and very cool approach. And here is the open source code for this project. It's the method about how to okay, we know that the chip is very important for the consumer and ICT industries. In the past 20 years, the chip technology has been greatly improved. The chip area and the energy consumption have been significantly optimized from 180 nanometers to the current 5 nanometers. And however, as the chip area shrinks, it becomes more and more difficult to upgrade this progress. But when we look at this table, we are surprised to find that the difference on energy costs and the required circuit areas for different operations are quite huge. For example, compare 8-bit multiplications with 8-bit addition, and we can see that there is a 7-fold difference between power consumption and the circuit area. That means there is still a lot of room to improve energy consumption and the circuit area through the innovation of algorithm, especially the deep learning methods. We know that the most commonly used deep models in computer vision are establishing using convolutional neural networks, and recently we have many works on vision transformers. Although they have shown excellent performance on a large variety of tasks, the basic unit in them is the calculation of multiplication and addition. So the initial idea for the adder neural network is that is there a calculation for deep learning that only includes additions? And the question here is that do we really need multiplications in deep learning? And I have worked on this project with a few colleagues and interns for about 3 years, and we can say yes to the above question now. Today, I will introduce 4 recent works we have done for developing adder neural networks with high performance and hardware verification. And the first one is it is presented in about 2 years ago. We successfully developed several adder nets with only additions in convolutional layers and got pretty good results on the ImageNet. And the second is a knowledge distillation for further improving the performance of our adder nets on the image classification task. The third work studies the low bit quantization, that is 8-bit, 16-bit integer values for representing weights and activations during the inference. And we also give the FPGA implementation for demonstrating the effectiveness for saving energy and the circuit areas of deep neural networks. The last one is our recent CVPR paper, which studies the application of AdaNet to the image restoration or maybe image processing tasks, and the results show that the AdaSR model can also perform well on several benchmarks. I will then orderly introduce these works, and the first work presents the detailed feed-forward and backpropagation used in our ADA neural networks, and this is there is also some interesting visualizations. We know that the deep learning is almost everywhere now. We can see many products using deep neural networks, for example, mobile phones, cameras, and autonomous driving. However, most of networks we used exploiting the same way to calculate the output features using both multiplication and additions. Let's first have a look at on this equation. X is the input data and F is the filter in a given layer. The output feature Y is usually calculated as the sum of multiplication results, or maybe we can regard it as a vector product. And generally, we also can see Y as the distance or similarity between any two X and F. If we normalize both X and F, the output feature Y is exactly the cosine distance. That is, we can distinguish different inputs using their angles from the normalized filter Y, F. So the basic idea came from some previous works in data mining. That is, we can use another distance measure to replace the conventional formulation without using the expensive multiplications. And there are so many distance measures, for instance, the Hamming distance, the Lipstein distance, wherein the Manhattan distance, as known as the L1 norm distance, is selected in our work to construct the deep neural networks, which has simple formulation and does not contain multiplications. And then we can easily formulate the gradients of both convolutional networks and the proposed AdaNet. Then we first conduct some toy experiments to obtain more observations for using the L1 distance. We can see from these figures, the L1 norm is also effective for learning filters with some interesting patterns, and the weight, and weight in AdaNet follows a Laplacian distribution. But if we directly modify the feed-forward and backpropagation from convolution to Ada, it doesn't work. And we notice some stranger phenomena during the learning of AdaNets. That is, the feature variance in AdaNet is very huge. Compared with those in the conventional convolutional network baselines. To better understand it, we thoroughly analyze the variance estimations of their features. From these two equations, we can find that the feature variance of convolutional network is related to the product of variance X and variance F, while the feature variance in AdaNet is related to the sum of the variance X and the variance F. So if we train a deeper network, this variance will be continuously accumulated. So we further display the gradients in both AdaNet and convolutional network with the same network architecture, and find that the gradient in AdaNet during the backpropagation is very, very small. So the overall network cannot be trained effectively. The reason is that the larger variance is not good for the batch normalization. To address this problem, we then develop an adaptive learning rate strategy with a gradient normalization to eliminate the effect of feature variance, which is now used for training most of our ADA neural network models. Then we can train the AdaNet as well as the convolutional baseline with the same architecture. And here we can see the feature visualizations of both AdaNet and convolutional net on the MNIST dataset. To draw these two figures, we set the number of neurons in the last layer as 2, and the features belonging to different categories are labeled with same color. Basically, this visualization is very interesting. The feature learned using AdaNet is similar to that of some clustering results of some data mining algorithms such as k-means, and the convolutional nets feature presents the different pattern, but as I mentioned above, we can regard the feature calculation as a distance measure, and the AdaNet utilized the L1 norm, that is the Manhattan distance. So we have this interesting figure. And then we conduct a series of experiments on several benchmarks models and this size, such as ResNet, VGGNet, and some data size such as CFAR and so on. And the results are quite promising. We replace all layers except the first and the last layers in these models by our ADA layers. And we can see AdaNet can also obtain similar results on the ImageNet compared to the convolutional baselines. For example, we achieve 91.7% top 5 accuracy on the ImageNet using the conventional ResNet 50 architecture, which is much higher than that of the binary neural network. Okay, the second work here is a knowledge distillation approach for better AdaNets. In the previous results, we can see there is still a small gap on the accuracy between AdaNets and convolutional networks. So we utilize a convolutional net here as a teacher to help the training of student AdaNet and obtain higher performance. Knowledge distillation is a very classical algorithm in model compression, which is widely used for enhancing the performance of the student network. That is the compressed model or a smaller model compared to the given teacher network. For example, we can transfer the feature information from the teacher network to the student network. And in the previous work, we show that our AdaNet can achieve an acceptable performance, but compared with that of the convolutional baseline, there is still small accuracy drop. So a very straightforward idea here is to utilize the knowledge distillation algorithm to further improve the performance of ADA network. That is, we use a convolutional network as the teacher and an AdaNet with the same architecture as the student. However, in most of knowledge distillation papers, although the architectures of teacher and student could be different, they are both convolutional networks. So it's uneasy for us to directly use them for learning better AdaNet. In addition, the weights and activation distributions in AdaNets are quite different from those in convolutional network. And that is the Laplacian distribution and the Gaussian distribution as shown in these two figures. To address this issue, we propose to embed a Gaussian kernel into teacher and student networks for reducing the feature divergence. In practice, activations, that is the output features of both teacher convolutional network and the student ADA neural network will be mapped into a higher dimensional space through the kernel. And then we further apply a one-by-one convolutional layer here to find the optimal transformation in the high dimensional space. Then the knowledge distillation is conducted at each intermediate layer to help the training of AdaNet, so that we can maximally approximate the performance of the convolutional network baseline. And the figure on the right side shows the pipeline of the proposed distillation method. Particularly, Both the student and the teacher network in our method are trained from scratch. That is, the distillation is utilized in a progressive way for fully investigating the useful information from teacher to student at a network. After applying the distillation algorithm, let's have a look on the features learned using different strategies. And it's very interesting that the visualized feature of AdNet using knowledge distillation have the properties of the baseline convolution network and the adder network. And these features can be distinguished by either the clustering centers and angles. In addition, we can see from their learning curves, the AdNet using knowledge distillation can surpass its baseline and on the safe-hearted sites. Then we evaluated the new method on the ImageNet. The results are in line with our expectation. Our AdNet can achieve higher performance with about 1% improvement on the top one accuracy. Even the enhanced AdNet performs better than the convolutional network baseline on the ResNet 50 architecture. Okay, let's move to the third part, that is the hardware implementation of the AdNet. To demonstrate the superiority of AdNet on the energy consumption and the circuit area, we conduct a series of experiments using FPGA, and the results show that AdNet with low bit quantization can significantly reduce the costs for launching deep learning models such as image classification and image super resolution. I have introduced how to establish and train an adder neural network and the distillation method for training adder network with higher performance. However, when we consider to deploy them on portable devices, we often need to quantize their weights and activations to low bit integer values, for example, 8-bit, 16-bit, even 1-bit, that is the binary neural network. Compared with floating number operations, the calculation of low bit values are much easier. And as mentioned before, the low bit integer calculation can maximally excavate the effectiveness of our AdNet. So we have to apply low bit quantization on AdNet for building energy efficient neural networks. And in convolution network, the scale factors for weights and activations can be commutative and fused during inference. For AdNet, we designed a shared scale for weight and activation, and we can apply the low bit additions inside the absolute value operation. Based on the low bit AdNet, we then designed the universal hardware accelerator on FPGA, and compared to the original kernel for convolutional networks with multiplications and additions, our adder kernel only utilizes additions, which is much cheaper for hardware implementation. And other parts, including data flow and batch normalization units, are the same for both convolutional network and the adder network for having a fair comparison. Experimental results show that the adder kernel with 8-bit values and 16-bit values quantization also exhibits a high performance and requires much less computational resources. When we increase the parallelized adder kernel with 16-bit quantization can reduce about 18% energy consumption. Since there is some costs on the other operations such as data handling and batch normalization, the whole network using adder kernel can achieve about 67% reduction. And we can further look at this table. With the new quantization scheme, the AdNet can maintain the original performance on the ImageNet benchmark. so that we can significantly reduce the energy consumption without affecting the network performance. Here are the quantitative results of the hardware implementation. We run an Ethernet and the original convolutional network with the same architecture on the FPGA development board and print the speed diagram of the two kinds of networks and their low bit quantization results, respectively. To maximally illustrate the superiority of our Ethernet, here we use a small net on MNIST, and all data handling is conducted on the FPGA platform. From these figures, we can obviously find that the fewer circuits are activated on the development board using either neural network. And in summary, we can reduce about 88% energy consumption on the convolutional layers using 16-bit quantized Ethernet and about 76 energy consumption using 8-bit quantized Ethernet. Similarly, the circuit areas, that is the number of lookup tables here, are reduced accordingly. Okay, the next is our recent work on how to apply other neural network in other computer vision tasks, especially the low-level computer vision. This work mainly studies the image super resolution problem, in which the input image is a low quality image and the desired output is the high resolution one. And fortunately, this work is accepted by ICLR 2021, and is another oral paper. In previous works, we present the use of Ethernet on the image classification task, which is the fundamental problem in computer vision. And besides the image classification, there is another very important topic, that is the image restoration for computer vision. And basically, image restoration aims to recover clean images from the input low quality images and contains several mainstream tasks such as image super resolution, image denoising, deblurring, and so on. To have an explicit illustration on the difference between image classification and restoration, we first print the feature maps of each layer for an image super resolution network. Different from the classification, we can find that features in different layers contain similar patterns, including both texture and color information. But the image classification network usually aims to generate features which can be easily distinguished by the classifier. And on the other side, I would like to emphasize that the computational costs of deep models for image restoration are much expensive than those for classification. So if we want to embed low-level computer vision models on our mobile phones using Ethernet to replace our original ones is a good solution. This work takes the image super resolution as an example, and the technique used can be also extended to other tasks. And although some verifications on image classification we have done, and if we apply the Ethernet on the image restoration, we will face some very difficult problems. The first is the identity mapping, according to this theorem, the Ethernet cannot directly implement the functionality of identity mapping, and therefore we propose a self-shortcut operation, which also involves the original input data X. By exploiting this operation, we can find that feature maps in the baseline Ethernet are very blurred, and some texture are lost, in contrast with the use of shortcut, features become clear with more outlines and details. And another important functionality of image super resolution is the high pass filter, which is often utilized to enhance the details for the output super resolution images. However, according to this theorem, we know that it also cannot be implemented by either unit. Thus, we develop learnable power activation in either SR models. By exploiting this new activation function, we can see that our AdaNet can learn features with clearer texture and age, and even higher feature diversity. After deploying the two new operations, we then verify the proposed method on two benchmark models and for benchmark this size. The results are quite promising. We can, using AdaNet, achieve very close PSNR and SSIM values to those of the convolutional baselines. And in summary, we can save about 60% energy for using these deep neural networks with comparable performance. In addition, we also provide a figure here to show the comparison of different models in terms of PSR values and energy consumptions. To further demonstrate the effectiveness of our ADA neural network, we also conduct a series of smaller models by directly reducing their channels. For example, cut by half and cut by 1/3. We can see that our AdaNet models can hold the best trade-off between PSR values and energy consumption, whether on large models or smaller models. And here we can also see some visualization results obtained using convolutional network and AdaNet. Actually, we cannot find obvious visual difference between them, but the PSNR values tell us that the ADA network can also be well applied on the low-level computer vision tasks with significantly lower costs, especially the energy consumption, so that we can embed deep models with powerful functionalities on our mobile devices, for example, the photography and the image generation. Okay, that's all of my today's presentation. You can reach more details from our papers and some open source codes from the GitHub page. Thanks for your listening.
Thank you for the great presentation. And thank you for keeping the time. So we can start with a few questions. And as usual, I think I will be the first to ask a question. So I guess that one natural comparison between AdaNets and other possible strategies is to compare with a binary weighted neural network, right? Because in that case, you replace the multiplications by additions as well. So is this something that you considered as a comparison point?
Sorry?
So you can binarize the weight in a neural network. So there are some strategies to do that. Just the weights, not the activations. If you do that, you end up with replacing all the multiplications by additions.
Okay, I see. That is a very good question. We list the results of 1-bit weight and 8-bit activation here. The accuracy drop is very very huge, from 91 to 89. There is about a 2-point accuracy drop on the ImageNet, the top 5 accuracy. However, the ADA neural network with 8-bit quantization can also perform well on the ImageNet with the comparable, almost we can surpass the ResNet 50 with 8-bit quantization. And that is the superiority of the use of our ADA neural network. Yeah.
So thank you for the answer. And I have another related question, is that when you introduced the model, it reminded me of deep RBF networks, which I think are quite similar to what you did. The main difference with the RBF network is that you're going to use a a decreasing function to transform. So basically, this is what you do, because if I followed correctly, you have a minus sign before the equation because you want the maximum activation to correspond to a perfectly matching between the line and the input of a layer, right? So I was wondering if there are some connections between your model and deep RBF models in general.
So basically, I think the the feed-forward equation in either neural network is very general, and we can embed the calculation of such a method in any kinds of neural network. For example, the convolutional network and some recent results we have done. We have successfully applied the adder neural network on the visual transformers and got some pretty good results, and some other clues on the maybe recurrent neural network is also fine for us to use.
Okay, okay. My question was not very clear. The thing is that there's a family of neural networks that do not use the usual multiplication that you have on the first row here. And they are called deep RBF neural networks. And what they do is that instead of doing the matrix product, they look at a function of distance between the lines of the matrix and the activation vector, the input vector. And I think that your formulation is a particular case of deep RBF networks. So it seems that it is particularly interesting because you have this this gain in terms of complexity. You don't have multiplications anymore. But I was wondering if there are more connections to the literature on deep RBF, because it seems to me that it's a particular case of deep RBF neural networks.
Okay, in my opinion, the L1 distance or the LP distance or something similar to this is not very new for deep neural network or for machine learning. The main contribution in our works is that we can use such a simple formulation to construct deep neural network with very high performance. We know that there is a number of variation. There is a number of different kinds of neural networks. So for example, the specking neural network. But the accuracy drop for using this for using them on the ImageNet is very huge. Yeah.
Yeah, I agree, and I think that your idea of trying to track the gradients is very interesting. I think it's a very nice contribution.
Thanks.
If
we do not modify the back propagation, the accuracy of either neural network is very low. Yeah.
So we have a question in the chat. So the question is, for training, the memory bandwidth is usually the main bottleneck. Are you aiming to move adder nets to even lower precision representations, especially for the activations? So there's a precision. So the slide 8 shows that you are using 8 bits. Have you done experiments, and how low can you go on the number of bits before the accuracy drops?
Oh, okay. So actually, here we show the 8-bit quantization for both activation and weight in adder neural network, and the performance of the quantized adder neural network is very close to that of the baseline full precision network. Yeah.